In this video, I'm going to present our work, Optimal Control for Clutch Elastic Robotic Systems, a Contact-Implicit approach. Let us begin with some background. Elastic robots, ER, show high performance and energy efficiency, but the timing of energy storage and release is not independent. With the use of clutches, this problem could be partially alleviated, leading to a new class of systems, so-called clutch elastic robots, CER. These robots offer improved control over the energy flow in the actuator. Recently, we also proposed a new clutch-based actuator concept called Bi-Stiffness Actuation, BSA. A BSA consists of a motor, here depicted in red, connected to a spring in yellow, a brake in purple, which can lock the spring element, and a clutch in cyan, which can couple or decouple the link from the spring. A challenge with this system and with similar systems is that the clutch sequence, i.e. when each clutch should be engaged or disengaged, is predefined. We therefore propose a new complementarity-based model for CER and a contact-implicit optimal control formulation to automatically resolve the clutch sequence. We validate our approach experimentally on a two-DOF system equipped with two BSAs using an IQR tracking controller. In the experiments, we aim to optimize the end effector speed at a final time of 0.5 seconds. We compare a predefined clutch sequence from our earlier work and an optimized sequence found by the new method. Before we move on to the experimental results, let us quickly have a look at the actuator modes. There are two main modes, SCA, Series Elastic Actuator, where only the clutch is engaged, and STG, Storage Mode, where only the brake is engaged and the link is decoupled. Let us begin with the guest sequence from earlier work. On the right-hand side, you can see a plot with the motor velocity in red, the link velocity in blue, and the reference generated by the optimal controller in green. Jet 1 starts in SCA mode and uses a resonant excitation strategy to increase the velocity. It then switches to STG mode at around 0.41 seconds. The situation is inverted in joint 2. It starts in STG modes and slowly builds up potential energy, which is released upon switching. Let us now have a look at the optimized sequence. Here, both joints start in STG mode and load their springs. The energy is then released in a sequential manner, at first for joint 1 and then for joint 2. While both sequences, the optimized and the guest sequence, lead to a similar final velocity, less control effort is used in the new sequence,